R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the Xxxi lecture series for the BSc Honours Physics students who are doing the 3-year full-time program. The paper 14, the paper is on optics, and the contents are shown in this slide. In continuation with what I have been telling you in the last lecture, we were seeing the Fresnel's half-period zones for plane wave and the explanation for rectilinear propagation of light. So, having said or having discussed so much about the ray optics or the geometrical optics and the wave optics, in which we have discussed about interference in a greater depth, then we move on to the phenomenon of diffraction. Let me tell you once again what we have to understand from the word diffraction, diffraction of light. Before I go further, let me tell you the contents of this lecture: the rectilinear propagation of light, half-period zones, resultant intensity inside the shadow. If one feels the geometrical optics is the right optics, who gave the ideas of geometrical optics? You all know that Newton gave the corpuscular theory of light. According to Newton, light travels in the form of straight line light rays, right? The light rays are traveling in the form of straight line. So, when the light is coming from a source, if I have got an obstacle, then the obstacle will stop all the light rays, will cut all the light rays, and light will be there above this is the obstacle, right? Above the obstacle, light will be going, and below that, there will be completely, there should be darkness. That is what you see here. You see here light is coming, you have got obstacle in the path of the light beam. So, the intensity is shown here, this is the axis, you have got intensity. Here, what do you observe here? The intensity is 0. There is complete darkness, right? You see here the obstacle is there. So, the light is, this is the obstacle here, right? So, the light is being cut off. You see the light rays are coming only in this region. Only the bottom region light rays are coming, because the top region is obstructed by the obstacle. You have got obstacle here that obstructs the light rays coming from the source. So, the light is cut off. Here this region there is light is cut off means what? What will you observe there? There will be darkness. Darkness cast by the object. So, you got a shadow, or the region will be dark. This region will be dark and this region will be bright. Restrict the passage of light. Light is coming directly, right? This region light is coming directly and falling on the screen. You know, as I told you, you find the intensity along this axis. There is something like graph drawn between intensity and the distance and the y axis. You have got the object here, okay? You have got the object. So, the intensity becomes 0 here. Here the intensity is a larger intensity, okay? Light can't turn around a corner. Who said that light cannot turn? It was Sir Isaac Newton who said light cannot turn around a corner. If you treat the light beam as if they are made up of rays of light, and rays of light travel in straight lines, then what Newton said is right, then you should have this kind of thing. But in reality, what happens is, as I told you in the last lecture, if you take a blade and have the blade in the path of the light beam, you got a source of light here, you got a blade, then you see them a diffraction pattern, right? A diffraction pattern whenever you got an obstacle, and the obstacle is a sharp edge, then you see some light seen where? In the region where you should have shadow, in the region where you got no light, you should not have any light, you should have darkness. In that dark region also there will be some light. So, light is really what is happening is so-called physical optics. It was observed first by the Italian physicist by name Francesco Maria Grimaldi, who lived from 1618 to 1663. He showed that light actually bends, it turns around the obstacles. So, you got obstacle here similar to what I showed earlier, you got obstacle here, and this region, you know, the intensity here should be 0, right? This is the intensity. You measure the intensity, okay, this is 0. The light intensity is 0 because you got obstacle here. You got obstacle, the intensity should be 0. Here it should be completely bright. But what you find is, in this region, okay, light is there, but in this region also there is some light. What does it mean? Light really bends around the obstacle. You look at the edge, this is the edge, light is coming here. In the earlier case, I showed I had only a straight line, right? There is a rectangular box like thing. The intensity is uniform, and then it abruptly falls to a 0 value. Intensity is uniform. Then at the edge, because you got obstacle, then exactly at the edge, corresponding edge, the intensity becomes 0. Then thereafter, obviously, the intensity should be equal to 0 because light is obstructed by the obstacle. Is that right? So, that is what you observe here. You see the intensity is 0 here, but contrary to what was expected by Newton or by other physicists who lived prior to the phenomenon of diffraction, which was observed by Grimaldi. Now, Grimaldi observed in the shadow region also, this is a shadow, right? In the shadow region also there is some intensity. That is what is called the thing giving rise to so-called diffraction bands. You have a fewer bands, you know that the interference bands, I gave number of lectures on the interference bands, wherein two light sources, the coherent sources, the light coming from the two coherent sources, they interfere, giving rise to what is called the interference pattern, which was observed experimentally by Thomas Young, and the theory was given by Huygens and Fresnel and so on. I will come to Huygens principle a little later, that whatever that light propagation, the theories which are propounded by Huygens, advanced by Fresnel, experimentally verified by Thomas Young, these people were able to explain the phenomenon of interference. Now, in the lectures to come, we try to understand or we try to explain the phenomenon of diffraction. So, what is diffraction? Diffraction simply means bending of the light beam. Because light bends, what happens in the region where there should be darkness, in the darker region also there some intensity is there. The intensity you see, it comes down. You got in the case of interference bands, I will compare the interference bands and diffraction bands a little later, but in the case of interference, you got a bright band, dark band, bright line, dark line, or band or line. You got a bright fringe, a dark fringe, bright fringe. The intensity of the two successive bright bands or fringes will be the same. Any two bands you can, or any two fringes you can take, the intensity will be the same. But here, what about intensity? You see, you got the intensity here to this extent, and the next region, you got again a band, the intensity has come down, right? This point is important point. In a phenomenon of diffraction, when you talk of diffraction bands, the intensities will not be equal, right. You see the intensity here larger, intensity is smaller. Again, this region, what about this region? In the earlier case, I showed them uniform intensity. Intensity is uniform because the light is coming straight. The intensity should be uniform. But now, because the light beam bends around the obstacle, right, what happens is, in the region where you should have complete darkness, instead of complete darkness, you get the so-called diffraction bands. Similarly, in the vicinity of this region, again around the obstacle, where you should have uniform intensity, there is a stepwise function. The intensity fell from a higher value, it dropped to 0 in the earlier case. That is what was expected by Sir Isaac Newton and others. But what Grimaldi showed is the following. The intensity in the region where should be high, in this region also the intensity, is not uniform. It waxes and waning and waxing. You got higher intensity, the intensity comes down, again intensity here, intensity is coming down. So, this region where you got the intensity should be falling stepwise manner. You got intensity here, the intensity drops to 0 in the shadow region. This is the shadow region. Here it should be intensity like this. The shadow region, it should be sharp drop. Thereafter, it should be intensity should have been 0. But here you got some intensity variation here. Here also intensity variation. So, around the obstacle, the point should be understood in a clear fashion. Around the obstacle, around any obstacle in the path of the light beam, the intensity will vary, and this gives rise to what are called diffraction bands. And you see the very many colors in a CD. You got take a CD and see the CD in the light, in the path of the light beam, in any room. When you change the position of CD, as I told you in the last lecture, the color varies. The variation in the color of a CD or the color of the birds, the feathers have got different colors. And again, what you find here in the case of straight edge or a blade, you have a blade, then you'll be getting the diffraction bands. It may be a circular aperture. We'll be dealing with all the cases in detail in the lectures to come. If you shine light and the light is passing through a small circular aperture, it may be a circular, elliptical, whatever the shape, a smaller aperture, a opening through which light is coming, that will give rise to diffraction pattern. A blade in the path of the light beam or a straight edge or a diffraction, a wire, we will be seeing all the cases in a detailed manner in the time to come. But now, the most fundamental thing is, what is diffraction? Diffraction is nothing but the bending of the light beam. Now, the question is how to explain the propagation of light in space. You all know that according to Sir Isaac Newton, light travels in the form of rays, the geometrical optics, right? You have got a light source, the light will be coming in the form of ray concept. So, that is the reason why it's called geometrical optics. You can draw triangles and so on, and so you can look at the various mathematical relations. You have a convex lens or a concave mirror and so on, where the image is formed, where is the object kept, and all these things, and you try to arrive at various formulae wherein you assume light, in the high school you would have studied, you have a concave mirror or a lens, the rays of light are passing through this, and then you get the image, inverted image, vertical image and so on. So, the ray concept is wrong. It cannot be accepted. As I told you repeatedly, there are phenomena like interference, diffraction and polarization, wherein the geometrical optics completely fails, and one has to eventually make use of the wave theory of light. Light is made up of waves. So, when you talk of light waves, people ask the question, how do you explain the propagation of light? How do you explain the propagation of sound? When I am talking, as I told you, you have a medium. If the whole room is evacuated, if there is no air at all, then I am talking, the people who are in front of me will not hear anything, because the whole room is evacuated. There is no air to propagate whatever I am talking. The sound is getting propagated from the person who is speaking to the person who is listening. The sound wave travels
through air. Similarly, light requires a medium according to Huygens and Fresnel, the people who lived long back, they expected for light propagation also a medium is required. And what is the name of the medium? That is the ether medium. But in the previous lectures, I told you about the Michelson-Morley experiment. It is a Michelson-Morley famous negative result experiment. We showed that ether is not present. So, let us have a break at this point. Welcome back after the break. We have been talking about the phenomenon of diffraction. In order to understand the phenomenon of interference, diffraction and polarization, we make use of Huygens wave theory. Let us try to understand the basics of Huygens wave theory. You have the slit, light is coming. I will go back. You see them. The light waves are coming, right? It is called a primary wavefront, right? Now, the envelope or the tangent, right? This is the tangent that you are taking, that gives the primary wavefront. The propagation of light wave follows the periphery of the wavelets. This is the periphery, right? From the periphery again, every point here will act as a secondary source, and they in turn will emit this kind of waves. Then once again you take the envelope, and then again take the envelope. That is how the wave is getting propagated. This is the primary wavefront. From the primary wavefront, the centers will act as source of disturbance. They emit what are called secondary wavelets, and the envelope of all the secondary wavelets will give the advancing wavefront. From the advancing wavefront, another advancing wavefront will come, and that is how light is getting propagated according to Huygens and also Fresnel. Okay, Huygens, listen to me, just add the wavelets considering interference, right? Of course, the wavelets are interfering. So, you have them, you go to the era of Huygens and Fresnel. Therefore, if one perturbs a plane wave front, the Huygens wavelets will no longer constructively interfere at all points in space. Adding the wavelets by physical optics explains why light can turn around the corners and create fringes around the images of objects. I told you in the last lecture, you got a light source here. From the light source, you got a wave front, right? This is what I told you in the Huygens-Fresnel principle just now. You got a wave front. From the wave front, you got another wave front and so on. So, when you go to large distances, at larger distances, a part of the primary wavefront, a part of the wavefront, a spherical wavefront, from that a part of it will become plane wave, right? I told you in the last lecture also, you take a big sphere. When you take a big sphere, take a small area, a part of a spherical wavefront will be a plane wavefront. This is a plane wavefront, right? So, this particular thing should also be kept in mind, because you are going to construct what are called half period zones, and then we will proceed further to show what is the final aim of the talk or final aim of this lecture. It is the lecture will finally end up to explain the rectilinear propagation of light or the formation of shadows, how shadows are formed. I told you in the last lecture, you got light is here, I got a finger, I get a shadow. How do you explain the formation of shadow, right? Okay, I will come to that again. Now, you got a plane wavefront, from spherical wavefront, you got a plane wavefront. Now, we want to understand the crux of the problem is the following. You got a child standing in front of a wall, you got light is incident, and what is diffraction? Light will be bending, light around the edges of the body will be bending. So, you will be tempted to ask the question, how will you get the shadow? Because if you say light is going to bend, the light should have bent, and the light should be coming from in this region also. Light should be coming from this region. When the light is incident on the left side, it should have bent. and the right side also should have bent. Everywhere light should be bending. If light is bending, then light should be coming here, right? Bending means the light should be coming. What happened to the light? How do you get darkness? Instead of having, because the light is bending, sound is bending, right? I will come to that again. Sound is bending. That is the reason why when I am talking from one room, the other person can, person walking in a veranda can listen to what I am talking here, because sound is bent. Similarly, if you say the light rays are bending, then how will you explain the shadow, or how will you explain the darkness in the shadow region? That is the crux of the problem, right? So, it spreads, which spreads? Light source, light spreads to some extent in the inner region, into the region of the geometrical shadow, because of the bending of the beam of light around the edges of a opaque obstacle. But the intensity, this is a point to be understood, but the intensity of light inside the shadow is extremely small, and hence it looks as though light travels in the form of straight lines. It looks as if it travels in the form of straight line. I have the finger here. If light is falling here, falling here, the bending is there, but still the intensity of light inside the shadow region is extremely small, so that the intensity can be neglected, or intensity becomes 0. That is the reason why you get darkness. That is the one that we have to prove based on the wave theory. Now, the problem is to explain the rectilinear propagation of light employing the wave theory. What do you mean by applying rectilinear propagation? Rectilinear means what? In the linear means line, right? If you got a source, point source, light is coming here, you got object here, it incident here, it will give rise to, light cannot penetrate, right? So, you get a shadow, light travels in the form of straight line. So, you get a shadow here, right? The light ray goes like this, and light ray goes like this, a shadow is cast. That is what I showed you here also, a shadow is cast, okay? Light ray is going like this, light ray is going like this. But what happens if the light ray is, you say it is bending, then the question is, what happened to the intensity here? Now, you have to explain on the basis of wave theory. It is easier to explain the formation of shadows on the basis of corpuscular theory of light, on the basis of Isaac Newton's ray optics. If the ray is going, it will be obstructed, and so the ray is falling here without any problem. That is the light here. Here you get the shadow because light is, it cannot bend. According to, Newton, light cannot bend. But now really light is getting bent, and so if light is going to bend, then everybody will be asking what happened to intensity here. So, the intensity falling to 0 value, how do you obtain? That is the question before us. That should be explained on the basis of wave theory. What you are going to do is, you take a plane wave front and construct what are called half period zones, right? And the light coming from every half period zone, how they will behave. So, A, B, C, D, what I showed just now is the plane wave front, the A, B, C, D, the plane wave front. Now, the plane wave front, I am going to construct what are called half period zones. A, B, C, D is a plane wave front perpendicular to the plane of paper, and P is an external point. At that point, we want to find the intensity. I will show where is P in the picture to come. To find the intensity at P, the resultant intensity at the point P due to the wavefront ABCD, what Fresnel did was to construct what are called half period elements or half period zones. They are called the Fresnel zones, as I will show you in the picture to come. So, you got a point P is the primary wavefront, this is a plane wavefront. From the light has come up to this, right, the plane wavefront. At the point P, what is the intensity? If you got obstacle here, some obstacle is there, at the point P, what will be the intensity? Now, this entire plane wavefront is divided into what are called half period zones. How do you construct the half period zones? As I told you in the last lecture also, you assume P as the central point with B as the radius, you get the perpendicular from P to the plane wavefront, it ends up at a point O, the B, the distance connecting, separating P and O, right. Then take this B plus lambda by 2 as the radius, draw a sphere, that sphere will cut the plane wavefront at the point M1. Then you take b plus 2 into lambda by 2 as the radius, draw a sphere. That sphere will cut and will give rise to a circle on the plane wave front with the radius OM2. The first zone is having radius OM1, whereas the second zone will have radius OM2 and the third zone will have the radius OM3. What is the difference between the first zone? This is the first off period zone. This is the second off period zone. What is the difference between OM1 and OM2? OM1 is separated from P by B plus lambda by 2, whereas OM2 is separated by how much distance? B plus 2 lambda by 2. So, what is the path difference? The path difference is here it is lambda by 2, here it is 2 lambda by 2. So, the path difference is lambda by 2. A path difference of lambda by 2 will correspond to how much time difference? A time difference t by 2. So, the light coming from here, the path difference between these two light beams is lambda by 2. You all know by now what is meant by constructive interference, destructive interference and so on. If the path difference is lambda or n lambda in general, lambda, 2 lambda and so on, that will lead to constructive interference. On the other hand, if the path difference is lambda by 2, that will lead to destructive interference. And so, what I would like to emphasize, what I would like you to understand at this point, light coming from M1 and light coming from M2 will have a path difference of lambda by 2. You look at this point again, M1P. M1P is P plus lambda by 2. Okay. M2P is B plus 2 into lambda by 2. So, the difference is lambda by 2. When the path difference is lambda by 2, what do you mean by that? You got a crust here, you got a trough here. This is a lambda, right? The light is traveling in the form of waves. So, crust and trough and crust. What is lambda? Lambda, the wavelength is nothing but the distance separating two crusts, or the distance separating two troughs is lambda. That is the wavelength. How do you define the wavelength? Whether you are an electrical engineering person or mechanical engineering, sound waves or light waves or optical engineering or illumination engineering, okay, you have electromagnetic waves, electronics person. What is wavelength? Wavelength is nothing but the distance separating two crusts, that is lambda. The half of lambda by 2 means what? The distance separating the crust and trough. So, a crust is meeting a trough, that will lead to destructive interference. So, the point that should be remembered is light coming from the first half period zone. They are called half period zones because that will be a time difference. Light coming from this first zone and the light coming from the second zone will have a path difference of how much? Lambda by 2, right? A lambda by 2 path difference will correspond to a phase difference of pi. A phase difference of pi means when a crust is coming from the first zone, a trough will come from the second zone. What will happen if a crust and trough meet? If a crust and trough meet, they will destroy each other. Therefore, the light coming from the first half period zone will be opposing the light coming from the second half period zone. On the other hand, first and third, the light coming from the first zone and the third zone will be having how much is the path difference? 3 lambda by 2, here lambda by 2. That means full lambda. Full lambda means full wave. If you know if the path difference is lambda, 2 lambda, n lambda, that will lead to constructive interference. On the other hand, lambda by 2 is the path difference between two light sources, right? If the path difference between two light sources which are meeting each other, if the path difference is lambda by 2, 3 lambda by 2, that will lead to destructive interference. And so, we will now pass on to the summary session of this lecture. Diffraction is nothing but bending of light beam around an obstacle. Even if light bends around obstacles, Fresnel was able to explain the formation of shadows. He could show that the intensity of light falling inside the shadow is negligible. This is how he was able to conclude by splitting the plane wave front into half period zones, the intensity becomes equal to 0. We will now pass on to the question session. What is meant by diffraction? Question number 2, what are half period zones? Last question is why are they called half period zones? With this, we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.